Welcome to Ugo Piomelli. Ugo is going to talk to us today about some simulations over rough surfaces, but let me give you a brief introduction. So Ugo obtained his laurea from Napoli. Then he worked for a master's at Notre Dame and a PhD from Stanford. From 1987 to 2008, he was on the faculty of the University of Maryland, progressing through the ranks of the professorship there. In 2008, he moved to Canada to hold a Tier 1 research chair there at Queen's University in Kingston, Ontario. Those of us working in turbulence know him for a range of contributions, many articles, especially for work pertaining to large eddy simulation and interpreting the physics of turbulent flows. He's a fellow of the Royal Society of Canada, of the American Physical Society, Institute of Physics in the UK, and the ASME over here, Associate Fellow of ARAA, and the Editor-in-Chief of the Journal of Turbulence. So we're really pleased to have you speak, Ugo, and as I mentioned, I'm teaching a turbulence class this term, so I'm hoping to see most of my class here so that they can get the up-to-date version of rough wall simulations from you. So thank you, Ugo, over to you.
Thank you, Beverly. Thank you for inviting me. It's frustrating that instead of being in sunny Pasadena, I'm here with 9 degrees below 0 Celsius at least, but that's the way it works in the pandemic. So I will talk today about simulations of flows over rough surfaces. And first of all, I need to get the laser pointer working. And then after that, I have to acknowledge the support from NSERC and Hydro-Quebec and the work that my former students, Junyuan, Wenwu, and my present student, Tsiansis, have done, and I will be showing mostly their stuff. What's happening here? Okay, so as usual, I will give you some background. I'll tell you about the objectives of this talk, how I do things, and then I'll show some applications. I may not be able to talk about separating flows. We'll see how time goes, and then I'll conclude. So the reason to study roughness is that it's present in a very wide range of applications, starting from the pipes, such as this one, which where the motivation for the earliest experimental studies. You can see the ice formations on a wing leading edge. They also act as a form of roughness. And another example is a Francis turbine. Those are the ones that are used in hydroelectric power plants. And they sit there for 20 years, get hit by rocks, dead squirrels, and other things. And there is cavitation, there is rust accumulation, and they get very, the surfaces that initially are very smooth become extremely rough. So because of its importance, roughness has been studied for many years, starting with Nikuradze's experimental studies in 1930s. He had pipes coated internally with dense packed sand with height K. And he observed that the increase in the friction, so the increase in the pressure gradient required to drive the flow, depends on a single parameter, the ratio of the sand grain height to the pipe diameter. And if this ratio K over D is small, the sand grains are immersed in the viscous sublayer and roughness effects are negligible. In the intermediate case, they start protruding outside of the viscous sublayer and they begin to disrupt the generation cycle. Also, in addition to the friction drag, there is a component of drag due to pressure because the flow separates, and so there is a higher pressure in the front and a lower pressure in the back. And if K over D is large enough, these elements stick out of the viscous sublayer completely. They completely destroy the turbulence or alter the turbulence generation cycle, and drag ends up being mostly due to the pressure difference. So it's mostly form drag. And those three regimes are known as hydraulically smooth, transitionally rough, and fully rough. And For those who have taught undergraduate fluids for mechanical engineers, that's what the Moody diagram shows. The hydraulically smooth regime is dependent on the Reynolds number. The fully rough regime, in which the friction factor, the drag, the pressure drop depends on the form drag, which is not affected by the Reynolds number, has the constant friction factor, and the transitionally rough regime is kind of intermediate, has some dependence on Reynolds number, but less dramatic than hydraulically smooth case. Now, one thing that has to be remembered is that roughness is not like sand grains. And in fact, if you look at, say, the Francis turbine, you see that the shape is completely different from a sheet of sandpaper. You have these elongated regions that you have different behavior, different types of roughness, depending on whether roughness is due to cavitation or to impacts. Not only that, but if you look at various different parts of a turbine, the surface looks quite different depending on how the flow is in that region. If you have a gas turbine, the shape is again different, and you see very clearly a preference of the roughness elements that are aligned in the flow direction. If you have a sanded surface, the preferential directions depend on the sanding, so on the manufacturing of the piece. So the shape of the roughness is not always sand, and the drag depends on the detail of the surfaces to some extent. One measure of the drag is the so-called roughness function. If we plot the velocity profile in our usual semi-log scale, we have our standard log layer. If we do the same thing for a rough wall flow, the log layer is shifted downwards. It's shifted downwards because the drag increases, the free stream velocity does not change, so infinity over u tau must decrease, and that's this shift here. This shift is called the roughness function, delta u. So the larger the shift, the more the increase in drag, and we can use the roughness function as an analog to give us an indication of the change in the drag. Now, if you have different surfaces with the same average height k, you can get very different values of the roughness function. They change by 50% or so. So the different surfaces, in this case, I think the experiment used sand, mesh screen, and mesh screens. Depending on the surface, with a certain height k, you will have a different drag, a different increase in the drag. And that's something that's important to remember. We know other things about roughness. It doesn't only increase the drag, it also increases the wall normal fluctuations and decreases the Reynolds stress anisotropy. In a rough wall boundary layer, the normal Reynolds stresses are not as large compared with the wall normal and spanwise ones as they are in a standard boundary layer. Also, there is outer layer similarity, also known as Townsend's similarity. Essentially, what has been observed is that roughness sets the velocity scale. Since you have higher drag, u tau ends up being larger compared with the smooth wall boundary layer or channel or pipe or so. However, a certain distance above the crest, about 5 Ks from the wall, the turbulence statistics normalized by u tau, the new value of u tau, which is larger than for the smooth wall, collapse on the smooth wall data. So the effects of roughness are first to increase the velocity scale, to increase u tau, and second, to change the distribution of the Reynolds stresses, for example, but only in a layer that's not very thick compared with the boundary layer thickness. Now, most knowledge historically comes from experimental studies, PIV and hot wire anemometer mostly. The hot wire anemometers in particular are single point measurements. The PIV are not. The experiments have been carried out both with organized roughness. Organized roughness are things like cubes or square cylinders or meshes, and with realistic surfaces such as sand grain or the turbine-like surfaces that I've shown before. The experiments can go to fairly high Reynolds number, but in general, there is no access to the flow below the crest, except for experimental facilities like the ones at Johns Hopkins that have matched the refraction index so that you can shine your laser through the object itself. There have been issues with numerical simulations that were summarized in an annual review paper by Javier Jimenez in 2004. And at that time, the description of generic roughness, meaning not organized, so not square cylinders or sinusoidal eggshell shapes, is difficult. The more important limitations are the fact that you want your roughness height to be much smaller than the boundary layer thickness or the channel half height to avoid blockage effects. If delta over K is, say, 10, then your obstacle is 10% of the boundary layer thickness, and it's not roughness, it's an obstacle. And thirdly, that if you want to reach the fully rough regime, then K plus, the roughness height in wall units, K U tau over nu, must be order 100. Now, if K plus is order 100 and delta over K is greater than 20, that means that delta plus must be 1000 or 1000, 2000, something like that. And delta plus of 1000 is a channel with delta plus of 1000 can be computed, but it's not a cheap calculation. It can take several, at least with Canadian resources, plain channel at delta plus 1000 takes several weeks of the wall clock time extends to several weeks. So numerical simulations of rough wall boundary layers are difficult because of the cost, essentially. The fact that the Reynolds number has to be large enough and the roughness height must be small enough. Now, despite these limitations, there have been a number of very useful studies in the early 2000s. For example, there's been the work by Leonardi and co-workers and Orlandi and co-workers who used simple geometries and high blockage ratio and low Reynolds number. But despite this, they looked at the role of the form drag, and very importantly, they proposed the relationship between the roughness function delta U and the vertical fluctuations at the crest, basically the wall normal Reynolds stresses at the crest. Scotti in 2006 developed a model for sand grain roughness that worked in the transitionally rough regime, and that's the model that I've been using for many years, and you can extend it to the fully rough regime. Napoli et al. Looked at sinusoidal surfaces in the transitionally rough regime, and they highlighted the importance of the slope of the surface as opposed to the average K or RMS and so on. And when I prepared this slide, I noticed that everybody in here is Italian. And so I wonder if there is some subtext, Italians are rough or something like that. Now, recent calculations have been able to extend the envelope by looking at more realistic geometries, higher Reynolds number, and non-equilibrium turbulence. More realistic geometries are things like sand grain or irregular surfaces like the surfaces of the hydroelectric turbines that I showed before, or the work that Neil Sandam and Angela Busse have carried out, first at Southampton, and then now Busse is at Glasgow, I believe. Several people have looked at scalar transport. We have managed to get to higher Reynolds number of order 1000 or more, which carries us to the fully rough regime, at least to the lower part of the fully rough regime. And we have been looking at non-equilibrium turbulence. A lot of people have been doing that. This is work from my group, accelerating and boundary layers in adverse pressure gradient, wall jets, impinging jets, and rotating flows. The disadvantages of numerical simulations are that they're expensive. They're expensive because you want a fairly large value of delta plus, and you want a small k. A small k means that the grid must be small because you need about 10 points in each in the streamwise and spanwise direction to resolve one grain of sand. So you end up requiring several million grid points to resolve a piece of sheet of sand that's maybe 3 inches by 3 inches. It's difficult to get a large sample. The number of roughness elements in a domain is finite and not large enough to give you a smooth sample often. The advantages are that, first of all, that the flow inside the roughness sublayer is known. We can tell exactly what the contribution of the flow below the crest is. Also, we can separate the forces. We can separate the pressure drag from the viscous drag. We can look at the Reynolds stresses, their divergence, and look at the contribution of each of the terms in the momentum balance separately. Multi-point statistics can be obtained. Also, higher order statistics, turbulent kinetic energy budgets, for example, can be obtained. And you can do flow visualization and get your colored pictures that are so nice in your journal articles. So what I would like to do today, what's the time? Okay, is to show some cases, some work from my group that to highlight how the knowledge that you can generate from numerical simulation complements the understanding obtained from experiments. So I would like to stress the additional knowledge that you get from a simulation that is very difficult to obtain from an experiment, and how this type of knowledge can help us understand the physics of the flow. And the 4 cases that I look at are the flow inside the roughness sublayer. And I'll show how these numerical simulations can help us understand the physics through the added value that they bring. So the 4 applications I look at, maybe 3 if I don't have time. First of all, I'll talk about the wake field. I'll talk about surface characterization. If I have time, I'll discuss separating flows. And I'll talk about Reynolds analogy for rough wall boundary layers or rough wall flows. The simulations I've carried that I'm going to show have all been performed using my standard Cartesian code, which solves the Navier-Stokes equation. It's Cartesian, staggered grid, second order accurate with centered finite differences. It's a non-dissipative code. The time advancement is a semi-implicit second order accurate. And we can perform direct simulations or large eddy simulations. And the large eddy simulation, we have been using either the Lagrangian dynamic eddy viscosity model or the integral length scale approximation, which is a model that we developed in the last few years. And the code is highly parallelized and has been validated for a very large number of cases. We've been using it for 15 years now. We are very confident of the results. So what we do is we solve either the Navier-Stokes equations or the filtered Navier-Stokes equations, and we model the roughness using an immersed boundary method as was proposed by Scotti. Essentially, we add a force to the right-hand side of the Navier-Stokes equations, And the force, the purpose of the force is to bring the velocity to zero inside the obstacle. And so we apply the force at all the points inside a roughness element, and also we scale it down, but also apply it in the at the grid points in which the obstacle, the roughness element, in which the grid volume is at least partly occupied by the roughness element, and the scaling is done using the volume of fluid. This is what a typical sand grain-like surface looks like. And you can see the underlying grid. The underlying grid is, I'm showing here, I think, every 10th grid point in the wall normal direction and every other point in the streamwise and spanwise direction. The grid has to be finer than the typical roughness length scales. And the typical roughness length scales are the Taylor scale, the Taylor microscales. As you can calculate Taylor microscales for the roughness itself and the average roughness height. The roughness elements are basically ellipsoids with an equal axis. The ratio of the axis is K, 1.4K and 2K that are randomly oriented in and placed on the bottom wall. And you can see some of them are isolated, some of them merge with others, and so on. So let's start talking about the wake field. And we can compare a plane channel with a smooth wall and a plane channel with a rough wall. Now, if the wall is smooth, the plane average and the time average, if the sample is large enough, are equivalent. Whereas if the wall is rough, plane averaging and time averaging are not equivalent. So here, for example, I'm showing a plane parallel to the wall for a smooth wall and a rough wall calculation. And I'm showing contours of the streamwise, the time average streamwise velocity, which in this case is uniform. It's the same everywhere because the sample is large enough that the time average velocity is a function of y, normal to the wall only. In the case of roughness, that's not the case at all. Since you have those roughness elements, the velocity is zero in the roughness element, you have stagnation points, you have channeling regions of high speed like this one, where the flow finds a path between roughness elements and so on. Now, as a consequence of this, in a smooth wall, the average V and W velocity components are zero. And the X and Z derivatives of any statistical quantity is also zero. In the rough wall, none of these things is true. There is an average wall normal velocity, a time averaged wall normal velocity, and time averaged spanwise velocity. As for example, the flows has to go around the elements, there will be clearly time average W. And the derivatives in X and Z of the time averaged quantities statistics is not zero either. So if we look at the production term in the Reynolds stress equations, and in particular at the normal stresses, for a smooth case, the production of the U squared stress is not zero, but 2,2 and 3,3 wall normal and spanwise is zero. So that the energy goes from the mean flow into U squared, and then it's redistributed to V squared and W squared through the pressure term. In a rough wall boundary layer, none of those three production terms is zero on the other hand. So we have the mean flow puts energy directly into the wall normal and spanwise stresses, not just in the 1,1 component that then redistributes it through the pressure to the 2,2 and 3,3. But we have direct injection of energy from the mean flow into the Reynolds stresses. So this brings us to the triple decomposition. if you look at an instantaneous velocity field, and here it's the U component in the rough wall case, we always, we used Reynolds decomposition. And so we have a mean part, time averaged, and then a stochastic component, a fluctuating component. Now, in a plane, in a smooth channel, this time average component is only a function of y, whereas in a rough channel, it's not. So we can further decompose it into two parts. One is the part that the time and space averaged velocity, and the other one plus the spatial variation of the time average. So here we'll have the spatial average, the plane average of this quantity here. And notice that the plane average is non-zero inside the roughness elements because it's only a function of y. The spatial variation of the time average is the difference between the time average and the spatial one. And it's also non-zero inside the roughness element because the sum of this plus that gives us this, and this one is zero inside. So if the plane time and space average is non-zero, the spatial variation of the time average is non-zero with an opposite sign, so that the two of them cancel out. Those are known as the double averaged velocity, the wake velocity, and the stochastic velocity component. And so we have a triple decomposition that's not unlike the one that's used for to isolate coherent structure, the one that was proposed by Hussein and Reynolds many moons ago. Now, the result of the wake velocity is, the wake velocity has two important effects. First of all, that it generates additional stress terms, the dispersive stresses. The dispersive stresses are a function of position, x, y, and z, but not of time, so they're stationary. Also, there are additional production terms that appear. If you look at the production of 1,1 stress, you use U squared. There is the first term. The first term is has the stochastic fluctuations that are averaged in space, in time, and space. The angle brackets represent space averaging. And this is the term that's present even in smooth flows. And then there are two terms that depend on the roughness geometry, and they are lumped together into the so-called form-induced production. Those terms have the tilde in them. The tilde is the spatial variation of the time average, and the tilde is directly related to the geometry itself, so to the shape of the roughness, to the type of roughness, sand grain, or whatever other shape it has. There is a difference between these two terms. This is called the wake production. This one doesn't have a name, and I'll talk about it in a little bit later when I show some results. So I'll show now some results from turbulent channel flow calculations, and we have done both smooth and rough wall simulations. The simulations are ran at constant mass flow rate so that the Reynolds tau changes. That's one of the two options. I could also run at constant Reynolds tau, and then the mass flow rate would change, but for various reasons, we prefer this setup here. The roughness height is 4% of the boundary layer of the channel half height, which gets us in the fully rough regime, and the blockage effects are reduced. The ratio of delta over K is 25, which is within the range that Jimenez recommends. And these are results that have been reported in a paper by Sriansis and myself in the Physical Review Fluids. So these are the budgets of U squared and V squared. And I'm not plotting all the terms, so don't expect that they balance. They don't. I'm skipping stuff. But you see in the smooth case, in U squared, you have as expected, you have production, you have pressure, and you have dissipation. In V squared, you have pressure and dissipation. Pressure and dissipation. If you have the rough wall, and here and in further slides, I always I will show a vertical line, that's the crest. So this is the position of the crest, and this is the roughness sublayer. First of all, the magnitude is decreased. The magnitude is decreased because of the normalization. Everything here is normalized with U tau fourth and nu. So since U tau is increases tremendously, the production decreases, normalized production decreases. But you see that, especially in V, there is a contribution, the green one, from the form-induced production. The form-induced production is significant both in V and W. It's very small in U. So we have one additional production term that's about 1/3 of the pressure. So it's not negligible. And it gives energy directly into V squared and W squared. And by doing that, it decreases the anisotropy. The V and W fluctuations are larger compared to U, and decreases the anisotropy of the Reynolds stresses. Notice that it's much less significant compared with the main production mechanisms for U than for V, and W has the same type of behavior. The way that this destabilization occurs is through the wake field, essentially. This is a contour of the wall normal wake velocity. So this is the stationary spatial variation of the time average velocity. And the lines show the low speed streaks, essentially. So you see that those red regions, those are jets, basically ejections that are due to the presence of a roughness element. Basically, you have the flow impinges on the roughness element and is deviated upwards and sideways, and the upwards deviation gives you this red ejection. And you see this plane here is very close to the crest, but not exactly at the crest, so that I could show those black marks to show the crest of the tallest elements. But you see here, for example, that there is a jet here that's due to an element that's lower than this plane, but the ejection persists some distance away from the crest of the roughness elements. What these jets do is they break up the streaks. You see that the streaks in this case are quite a bit shorter than in a standard boundary layer. They're about 500 wall units long, most of them. There are some longer, but generally they tend to be about 500 wall units versus the 2000 or so for a regular boundary layer. You see here streamlines in the zooming on the roughness sublayer. This again is the wake component of V, which is equal to the time average component of V, because there is no plane average of V. And you see here how some streamlines remain kind of captured inside the roughness sublayer, but then you have the ones where the flow impinges on the roughness element that go up, become green here. And you also see some sweeps, the flow going into the roughness sublayer. And the sweeps tend to be less dramatic. You don't have this large vertical component, but they tend to be quite a bit larger because they, as they extend over the entire separated flow and recirculation region behind the elements. Here I'm showing span-wise velocity, and you see here, for example, red on one side and green on the other, because the flow is going to the upwards, well, to the right of the roughness element on this side and to the left on the other side. So you see that you also have this span-wise, stationary span-wise velocity spots all over the place. And we know that both the wall normal and the span-wise fluctuations have a very important effect in the turbulence generation cycle, as has been shown by a number of people, Jimenez and Pinelli, I think it's Sharma and Hussain for sure, and co-workers. So what the crest plane is, it's essentially, it's a slip wall with stationary ejections and sweeps. So stationary jets directed either downwards or upwards and sideways as well. So you see, you get this velocity. This is the time average velocity. You see the velocity goes all around these elements. You have jets and so on. And here the colors show the angle of the velocity vector, the elevation angle, angle of the plane. So you see you have regions where it's upwards and regions where it's downwards, corresponding to these jets and sweeps and ejections. These regions here looks like the angle is large, but it's because it's a ratio between two small numbers. The velocity here is almost zero in the recirculation region. And so as a result of all this, turbulence becomes more isotropic. So streaks are broken up by roughness. The V and W fluctuations are generated, and the turbulence production cycle is modified. And the wake fluctuations play a key role in this modification of the turbulence production cycle. And the wake fluctuations are intimately related to the geometry. So the type of roughness, sand grain, rusted turbine blades, or whatever, has different drag, and the different drag is due to the fact that the wake field is different. So in some cases, you see very vigorous ejections and sweeps. In other cases, less vigorous, and depending on that, you're going to get different drags. So either more or less drag for the same value of K, which brings us to the equivalent sand grain roughness. The equivalent sand grain roughness, Ks, is a way to parameterize the rough surfaces. Ks is the height of the sand grain surface that would give you the same drag as the actual surface you're looking at. So you have whatever surface you have, say a rusted turbine, you measure the drag, you look at how large would be the sand grains that give you the same drag, and that's the equivalent sand grain roughness, Ks. Now, one thing that's very important to know, to remember, is that Ks is a measure of the drag, so it has nothing to do with the geometry. It's a parameter that's determined by the flow itself. So the geometry creates drag through the wake field, and the Ks is a measure of the drag. Ks is essentially equivalent to the roughness function, at least in the fully rough regime. The roughness function depends only on Ks and not on the geometry, whereas in the transitionally rough regime, it depends on both. Now, one thing that's quite important is that the fact that in turbulence models used in the Reynolds equation, Ks is the only parameter that's used to describe the surface. And that's a problem. And that's a problem because you can have various surfaces with the same height, and these surfaces could have very different equivalent sand grain roughnesses. So they will have different drag, therefore different Ks, and a turbulence model cannot distinguish between them. This is work that was carried out by June Yuan, my former student. She's now faculty at Michigan State. And we looked at 4 samples taken from actual hydroelectric turbines that were supplied by Hydro-Quebec and compared them with the sand grain model. Now, what you can do is you can perform a number of simulations. You can essentially do the smooth calculation, which would give you a log law that sits here, and then look at do simulations with the resolved roughness, and you'll get, for the various surfaces, you would get different log law shifted down by certain roughness function. You can change the roughness height by simply scaling the geometry, the roughness surfaces up or down. And you measure the roughness function you redo this for a different height k, and then you plot your results, and you get delta u as a function of k for the various surfaces. If you require that delta u becomes independent of the equivalent sand grain roughness at the right end of the range in the fully rough regime, you can back out the value of Ks for all these surfaces. And you get something that looks like this. The sand grain is the one that has the steepest slope. So the ratio for a given K, you have the largest Ks, which means that it's the one that gives you the most drag. And then the others have decreasing values. You see that this surface here, one on the bottom right, looks kind of smooth. So even if you scale it up so that it has a certain value of K plus 40 in this case, it will have less drag than a sand grain with the same average height. Now, that's useful to know, and it's also important, would be important to find this relationship here, knowing only the geometry. And this can be done. There are various semi-empirical correlations that do that. You can have the relationship depending on the blockage, on the moments of K, on the slope of the surface, or you can use machine learning to determine this. This is work that's been done by Jun Yuan at her new place. But you need to determine what Ks is for a given K, knowing only the geometry, if you want to use a Reynolds stress model. So the difference between these two geometries, this one gives you intermediate values of Ks for a given K, this one gives fairly high values of Ks, is essentially coming from the wake field. Here we have a lot of stationary ejections that are distributed randomly. So you get a vigorous destabilization and a high drag, whereas here you have, even with the same average height, you have fewer stationary ejections that tend to be larger. The destabilization is weaker, and that results in a lower drag. So the wake velocity, the wake field, is the connection between the geometry and the changes in the drag and the changes in the Reynolds stress anisotropy. And understanding about the wake field, I think, can give us a better idea not only of what the value of Ks should be, but also on whether that's enough to represent roughness. And I think I'm going over time here. So let me skip this part and tell you a couple of things about the Reynolds analogy. The Reynolds analogy is the textbook relationship between velocity and temperature statistics, temperature being an example, but any passive scalar will do. Essentially, since the equations, governing equations are the same, and momentum and scalar are transported by the same eddies, one should expect that the statistics will be the same if a proper normalization is used. And that is true. You look at the relationship between Stanton number, skin friction coefficient, and it's constant. The mean velocity and scalar profiles scale very well. The velocity and scalar variances, and even the budgets of the Reynolds stresses and scalar variance too. But if the wall is rough, that's not the case, because while heat transfer is due to diffusion and always depends on the molecular properties, the drag if the flow is fully rough depends on pressure, on the form drag. So eventually it becomes independent of skin friction coefficient. And so if Cf is constant while Stanton number changes with the molecular properties, the ratio cannot be constant. And this is something that has been known for a while. And you see the difference here. This is taken from work done at Melbourne. Those are contours of instantaneous velocity and scalar for increasing values of the roughness. And the white line is a line of u plus equals 4 or theta plus equals 4. And you see here that there is a recirculation region, there is separation behind the roughness element. And so the y plus equals, the diffusive sublayer disappears, whereas for the scalar, it remains there. So we perform simulations, we get the standard results. There is a roughness functions for the scalar that is different from the roughness function for the velocity, and these are things that were well known. We look at the Reynolds stresses. Townsend similarity applies, so rough and smooth cases collapse, both for theta, for velocity, for u squared, for Reynolds stresses, and for variances. But what we see that's different is that while u squared decreases very substantially, theta squared doesn't decrease very much. And we wonder why that is. To understand why that is, we look at the budgets. This is the budget for u squared and for theta squared for the smooth wall case, the usual terms, production, dissipation, viscous transport, and turbulent transport. And we have the usual behavior. We see that if we look at the rough case, we see a different behavior. In particular, we see that the form-induced production, those magenta, it's called magenta, I think, those purple kind like triangles, is very much more significant for the scalar variance than it is for the Reynolds stress. And that's related to the flow field, to the wake field itself again. You see, this is the wake field, scalar field, and this is the wake velocity field. And you see regions where it looks the same, especially in the channeling regions between elements, and regions especially near the recirculation, in which it looks quite different. The recirculation regions here are quite extended, and here they're not. You can look at contours in the other plane, and you can get a lot of interesting things that I will not mention for time constraints. But the essential difference is the fact that the velocity gradient is significant only in the shear layers that is more significant in the shear layers that at the top of the tallest elements. The scalar gradient, on the other hand, is very significant even in those elements that are sheltered by the taller ones. So you see a lot of red here in the regions, in the recirculation regions. And as a consequence, the form-induced production of theta ends up being much larger than the form-induced production of u squared. So here we have another case in which the wake field plays an important role, and the difference between the wake field in the scalar and the wake field in the velocity goes a long way towards explaining the failure of Reynolds analogy. And this work leaves us with a bunch of questions. For example, the fact that you have a different roughness functions, does that mean that when you run a turbulence model, you should use a different Ks to account for the different effect of roughness? Also, since there is a larger contribution of the form-induced production, the physics are quite a bit different. Typically, Reynolds stress models are used for the scalar transport equation, are the same as the ones that are used for the momentum equation with a diffusivity that's changed by a turbulent Prandtl number. Here it seems that the physics are quite different. So that straightforward extension doesn't appear to be justified. Is Ks sufficient to account for the geometry effect? Probably not. Even two values of Ks, one for the scalar and one for the momentum, probably would not be sufficient to account for the effects of the geometry. So let me conclude by saying that I've shown some simulations with resolved roughness, which are obviously feasible. The Reynolds numbers are still moderate, not tremendously high, but they allow us to get to the fully rough regime. Getting to realistic values of Reynolds number is still infeasible because of the various constraints that I've mentioned. we get higher order statistics, and those can explain a lot of things, and we have access to the roughness sublayer, and those are advantages that we have over experiments. And I think that putting together the experimental knowledge and the knowledge about the sublayer that you get from numerical simulations can go a long way towards understanding the physics. Those, I think, are the two most important points. So that's it, and I apologize if I've gone over time, and I will be happy to take any questions.
Thank you, Ugo. Not at all. As I mentioned, we appreciate you leaving time for questions. So thank you for your very interesting talk.